Hello students. So in this chapter of electronics lecture, we will go into details of the stability factor that was defined in the last lecture. We were discussing the methods of biasing, about the transistor biasing, and we defined the factor called the stability factor. It is the measure by which you can estimate whether your circuit is stable or not. This is the significance. Basically, the stability factor, it is defined as the ratio of, or the ratio of the change in the collector current to the reverse saturation current, or ICO, at constant base current and at constant beta. So the stability factor S measures the extent to which the stabilization has been achieved. Now let us see in details what are the other factors, what is more about this stability factor, what information this stability factor is going to provide you. So this is the definition. So if we have a large value of S, this means the collector current, change in collector current is quite large with respect to the change in reverse saturation current or the leakage current. So if S is large, this means that IC undergoes a large change when ICO changes, when ICO, leakage current or reverse saturation current, whatever you can say, leakage current changes. So what will be the effect? The effect will be this, that if collector current is changing by a large amount, this will cause a large shift in the Q point. So as a result, Q point will not be stable, which is not required. Q point must be stable. Q point will not be stable for large S. If the stability factor is quite large, Q point will not be stable. So the circuit is unstable. This is an unstable circuit. It will not produce faithful amplification. So greater thermal instability is shown by large value of S. So you can say that large value of S indicates large thermal instability. This means that your circuit is not proper, it will not produce faithful amplification. So thermal instability is large for large values of S. That is why sometimes this stability factor is better called instability factor, but that term is not used. We use the term stability factor, and this is the usage that has been mentioned in almost all of the textbooks, so you have to define it as stability factor. Now the stability factor has an alternative derivation, has an alternative expression, and in this expression the equation that is used is stability factor is alternatively defined as, or you can say defined from the equation, this is IC is beta times IB plus 1 plus beta times ICO. This equation I have mentioned in the previous lecture. You can use this equation to find out this variation in IC. Now if you differentiate with respect to IC, what happens? DIC by DIC. Now you are differentiating this expression beta IB DIB by DIC plus 1 plus beta ICO DICO by DIC. If you are differentiating this, what will you get? Now this quantity we have defined DICO by DIC is S from the previous lecture, from the previous derivation. S is DICO by DIC. So this quantity is S. You can write this as S. So this equation will be DIC by DIC, of course it will be equal to 1 beta DIB by DIC plus 1 plus beta, and you have this equation here, it is S. It is 1 by S, sorry, it is 1 by S, because here you have DICO upon DIC. So this is the alternative expression. So from this expression, since this quantity is equal to 1, you can rewrite it as DIB by DIC plus 1 by S into 1 plus beta. From here you can get an expression for S, and that expression will be 1 plus beta upon 1 minus beta DIB upon DIC. This is the alternative expression for stability factor. Now why this expression is used? Why it is used? Because this expression will help you in the practical circuits. For any circuit, when you are doing the experiment, during experiment, the equation for stability factor that you generally use is S is 1 plus RB by RE. This is for experimental purpose, the base resistance and the emitter resistance, and 1 plus 1 minus alpha RB by RE. This equation is used for practical purpose during the experiment. The alpha value will be given to you. You can measure RB and RE in the circuit, and then you can put in this equation to find the stability factor when you are doing any particular experiment of bias stabilization. So this is the alternative expression. RB is the total series and parallel resistance in the base, total resistance in the base. RE is the total DC resistance in the emitter, and alpha is the alpha parameter. Now another important parameter that is defined here, that is called the beta sensitivity. We learnt in the last lecture that the transistor parameters beta, VBE and collector reverse saturation current, they are strongly affected by the temperature. So beta sensitivity of a circuit implies, or it means, the influence that the beta value has, the effect of the beta value on the DC operating point. What is the effect of beta? Sensitivity means how does the DC operating point change with beta. So this parameter explains how does the DC operating point, that is the quiescent point, and it is the most important factor, DC operating point change with beta. This is the information that is provided by this beta sensitivity. So if beta values are changing due to circuit operation, or if you are changing the transistor, suppose you are working with one transistor and the transistor is damaged, you are changing the transistor, then the beta value is also changing. So the beta sensitivity, which is generally called K beta, it is defined as K beta is called the beta sensitivity. Beta sensitivity. And this K beta, it is DIC, change in the collector current for a given collector current, and it is K beta DIB by beta. So you can find out K beta as beta upon IC, and DIC by dIB. This is the beta sensitivity. In many of the cases you are asked to find out the beta sensitivity, so you can make a conclusion about the stability of that circuit with respect to beta. Now let us let us come to the stability factors for different circuits, mostly the CB and the CE configurations. So we are starting with the CE circuit because this is mostly used. There are many other aspects of the CE circuit, but this was demanded by some of the students, so I am discussing this first. Now in the CE circuit, the collector current IC, I have told you it is this same equation, IB plus 1 plus beta and ICO. If you are asked to find S, how will you find? We have discussed DIC by DICO, and you have to differentiate it. Now this, when you differentiate it, this is 1 plus beta, because we are considering beta and I beta as constant, so ICO there will be a variation 1 plus beta. Now see, in general beta has a value of 100 or more than 100. This is a very less value. Beta is generally 250, 300, this type of values are observed for beta. So in this case S will be equal to 101. So you can see that if there is a change in the reverse saturation current, the collector current changes 101 times. For a change in ICO, IC changes 101 times. So this is highly unstable. You have to stabilize the circuit. In case of CB, if we consider the common base circuit, in this case, what you have to do, you have to use this equation, IC is equal to alpha IE plus ICO, and when you differentiate IC with respect to ICO, it is equal to 1. So the stability is much less. Now we have to see what are the different arrangements for stabilizing the circuit, or what are the different biasing circuits that are used for stabilization. And the most important thing that is asked many times in the examination, that on what factors does Q change, or on what factors does Q depend, or how Q changes for a given circuit. So Q depends on mainly 3 factors, that is the reverse saturation current, and this saturation currents double for every, it becomes 2 times for every 10 degree rise in temperature. Next factor is the base emitter voltage, and there is a decrease of about 25 millivolts per degree Celsius. And the next factor is beta or HFE, that rises with temperature. These are the main factors on which Q depends. And you have to stabilize Q, you have to make Q stationary as far as possible against the changes that are occurring in these factors. Now what are the methods of transistor biasing? There are in general 2 methods. One is the stabilization method, other is the compensation method. In stabilization technique, we refer to the techniques of resistance biasing or resistive biasing circuits that allow the base current to vary and keep the collector current with respect to the changes in reverse saturation current, beta and VB. So whatever change is occurring, that change is occurring in the base current, and IC has to remain constant with respect to changes in these 3 parameters. The next type of circuit, point number 2, is the compensating circuit or compensating techniques that refer to the use of some temperature sensitive devices like diode, transistor, thermistor. What these devices do, these devices, they provide compensating voltage and current, means they make up the changes in voltage and current that maintain the stable operating point. For practical purpose, we have four methods of bias stabilization. This one is the base resistor emitter bias, biasing with collector feedback, and fourth is voltage divider bias. The basic thing of all these circuits, or the basic principle that is used in all these circuits, is to obtain the base current IB from the VCC or the DC battery that is connected to the collector N. Base current is not obtained from the signal, from the input AC signal, that has to be varied. This is the basic principle of all these circuits. Without any input current or signal, means I am showing you the circuit. This is the circuit. The base current is provided by this battery, that is the VCC, the battery that is used to reverse bias the collector N. You are not obtaining any current from the input signal, so it is written here without any input signal. And what you have to take care is that the collector emitter voltage must be larger than 0.5 for germanium, and it must be greater than 1 volt for silicon based transistors. We will discuss the first method, the base resistor method. This is the circuit diagram of the base resistor method. I will show alternative diagrams also. What happens in this method? We have a high resistance RB, and this RB is of the order of several kilo ohms. You have to take this in consideration. Several hundreds of kilo ohms, and it is connected between the base and the positive end of a NPN transistor. You can see in the diagram, this is a NPN transistor, this is the P part, and you are connecting this resistance at one end should be connected to the P part, and the other end is connected to the VCC. For a PNP transistor, what will you do? One end of this base resistance, it will be connected to the N part. You have to take this thing into consideration. I will write it. Wait, first let me explain. So, the required zero signal base current, it is provided by this VCC. You can see the diagram. This battery, which is used to reverse bias the collector N, it is providing the base current. The base current should not be provided by the input signal. The required zero signal base current, it is provided by the DC battery VCC, and it is flowing, and that current is flowing through RB. Let me write the description. The base current is provided by, you have to take this thing into consideration when you are joining the circuit, when you are doing the experiment. The base current is provided by the VCC that flows through RB, that has several, that is of order of kilo ohms. It is not provided by the input signal. Times and again I am telling you. In many cases I have seen that students make this mistake. It is because now the base, you are using a NPN transistor here. Now the base is positive with respect to the emitter, that is the base emitter junction is now forward bias, that is required. Now the required value of zero signal base current, it is flowing through the base resistor, and you have to choose this base resistor properly. How will you choose? Let us do the circuit analysis. Now in this circuit analysis, what we are mainly required to do is, let me change the page. In the experiment, what you have to do, we need to find a proper value of RB. This is the base resistance that we have to calculate, so that the required collector current flows in the zero signal condition without any signal, so that IC flows in zero signal condition. We have to get a output current without zero signal, then only you can fix the Q point. Sorry, in zero signal state or condition, whatever you say, then only you will be able to fix the Q point. Now if IC is the zero signal current, you are well acquainted with this equation. This is the definition of beta. Beta is the ratio of IC and IB, and you have to use this equation. So this is the equation. Now if you consider the circuit, here the circuit, it is this A, B, E and A loop. A, B, E and A loop. If you are considering this circuit, this loop, the Kirchhoff's voltage law gives this kind of a equation. And from here you can calculate the RB, and this RB is VCC minus VBE by IB. This is the value of base resistance that you have to use. Before joining the circuit, you have to do the calculation. Without calculation, you cannot perform the bias stabilization experiment. So your VCC is given, IB is given, and VBE you can obtain it from the transistor manual. What value is given? It is for germanium or it is a silicon transistor. You can obtain the value of RB. As now this VBE, it is much smaller compared to this VCC, so you can simplify this equation and you can write this as RB is equal to VCC minus IB. Again I am telling you that you have to do the calculation before experiment. You have to do the calculation before experiment. Without calculation you cannot obtain RB. You cannot arbitrarily choose RB. So VCC given, VBE you can get from manual, transistor manual, and you have to put these values to obtain the value of base resistance that is required to make a flow of current in zero signal condition. VCC is fixed, known quantity, and IB you are choosing some suitable value. This method is called fixed bias method because IB is fixed. IB is fixed to some value. VCC is known, so it is called fixed bias method. This is also known by another term called fixed bias, because you are fixing the base current. This is the significance. So again you must complete these calculations before going to the experiment, before joining the wires, otherwise your experiment will not be proper. Now let us calculate the stability factor. Stability factor, this is the main part of the experiment, to calculate the stability factor. So how can you calculate the stability factor? We have obtained the relation beta plus 1 by 1 minus beta DIB, let me correct it, DIB by DIC. You have obtained this relation. In the fixed bias method, IB, it is independent of the collector current. Base current is fixed, it is independent of collector current, or you can say, since we have fixed the value of base current, so this quantity is going to be 0. This quantity is going to be 0. Let me write it as IB is fixed So dib by dic is equal to 0. So what you get? S is equal to beta plus 1. Now as I told you, if beta is 100, then S is 101. This means the collector current is changing 101 times with faster than the reverse saturation current. If you take beta is 100, S is 101, IC is 101 times faster than ICO. So we can say that this circuit has poor thermal stability. S should be 1. Ideally you cannot get 1, but it should be as less as possible. Poor thermal stability. This circuit is totally not good for proper amplification. Though it has some advantages, it is very simple and you require only one resistance. Calculations are simple. These are the main two advantages, but the disadvantage is that the poor stabilization is very poor. Because you have no way to stop a self increase or the automatic increase in the collector current due to temperature. Now suppose if you are changing the transistor, beta is changing, then IC will also increase by the same factor as base current is constant. And due to this high stability factor, high value of S, there are chances of thermal runaway that I explained in the last lecture, and it can damage your circuit. So you are not going to get proper amplification by this circuit. So fixed bias or base resistor method is not at all a good or properly stabilized circuit. Now what are the other methods and which is the best method, we will see in this next lecture. And after that, if time allows, we will go into some calculations that are very essential. At the last, I am again telling you that without calculation you cannot perform this experiment. First you have to find the RB. I will soon come with the other parts, other types of bias circuits, and we will discuss which one is the best. So for the time being, stay tuned and please watch the videos. They are for you, they are for your betterment. And like, share and subscribe. Thank you.